Um, Welcome. Well, I'm calling from Alaska, so it's about 15 degrees. That's why I have a jacket on. Okay, so let's go to my first talk, which is uh, electric discharge evidence found in Pook's Pebbles, which is a new class of Chicxulub ejecta. On the first slide, you can see what I am talking about. These are the pebbles. They look rather ordinary, but they have very interesting properties, both morphologically as well as compositionally. And so just remind you where's the location. It's the famous Chicxulub impact site. And in this, I hope you can see my pointer. There's Albion, Island Quarry, and Pook's Hill Lodge. That were our sampling sites where we collected our specimens. Down here, you have a profile, like a profile that kind of shows you how where it is, how far it is in respect to the Chicxulub crater. It was in a Belize location, and Albion Island is fairly far from the center of the impact. And this is like a beautiful site of the Albion quarry. If you look at this slide, you can see that there is a very spectacular formation. You can see this yellow horizon, which is the spheroid bed. This is the first deposit of ejecta deposit that was deposited on the Barton Creek dolomite formation. And then about this yellow layer, there's diamectite. And so we will be talking about object that we collected from the spheral bed. And then we also found these very spectacular other type of ejecta objects. I mean, we are here like 350 kilometers away from the center of the impact. And as you can see here, there is Adriana for scale. And this is the block which was deposited 350 kilometers away from the impact. So must have been very tremendous ejection that was able to, I mean, get this large block and move it so far. So the way I'm trying to do this talk is that I will like always show what we discovered and what's the evidence for it. So one main thing we found that Pook's pebbles were formed by particle interactions and collision as the ejecta passed through the near surface debris cloud and struck the regolith covered Cretaceous land surface. And the reason for that is because the Pook's pebbles surface features are superimposed with ablation features that I will show in the few slides. This is one of the pebble. You can see from like all different directions, and it looks like ordinary pebble, right? You don't see like anything special, maybe except there is a little like a groove that I mean you can find here, but it doesn't look like so special. But now when you look closer, that you find that a lot of these pebbles have these indentations, like a thumbprint, kind of a peculiar. Now, when you look on further to the surface, then you'll find out another features. Like, for example, on these two pebbles, you can see that there is some kind of like lineation. I mean, if you can see on this right-hand side, on this figure, embedded within the pebble. When you look even closer, then on some of these what looks like striations, you can see that there are these like a sets of striations that appear to be in like some angle, like a parallel grooves that appear to be some sort of like a friction must have happened between the surfaces of these pebbles and something else. Now, and when you look even closer, then you find that these pebbles are mainly like carbonaceous pebbles, and so the crystal of calcite are fused together. I mean, this is a fairly like a small scale. You can see the scale like a 2 micrometer, and you can see that these crystals very often are, I mean, they're just fused together. They are not like separately, uniquely separated. Okay, so the next thing is that Pook's pebbles require, in order for their mass and for the size, ejection velocities 1 to 2 kilometers per second, and they had to reach altitudes of approximately 100 kilometers. I mean, 100 kilometers is high, right? It's like 10 times the airliner is flying 100 kilometers. I mean, this is just, I mean, when you do like a simple like a kinematic equations, and you are trying to, if you want to do it more precisely, you put the density of the air and drag force, and then you can find out, I mean, what's the trajectory of these Pook's pebbles have to be in order to reach from the center of the Chicxulub to this location in Belize. The Pook's pebbles experience the overpressure on their surfaces up to 500 megapascal. The evidence for that is that once you cut the Pook's pebble, like you have a Pook's pebble, you just cut it with the saw and make the thin section, then you find that some of the surfaces actually have a twinning, calcite twinning. Just this is the surface of the pebble, and you can see that there is a that there is about 100 to 200 layer of calcite that appears to be twinned, as opposed to the rest of the calcite that do not show that twinning. So that would be indication that there was some like a recrystallization process as a result of pressure and temperature increase. The next, what we found that ejected impact glass from Chicxulub can be found with magnetic sensors on future planetary rovers. And this is because the devitrified glass has enhanced paramagnetic enhancement. When you look at the, when you're like a spheroid bed, or when you look at the objects that are within that yellow layer, this is an example. You can see that there's an intricate mixture of like a major elements. There is devitrified glass here in green. Then there is a white spheroid. Then there is a limestone, these kind of like a gray grains. And there is a pink spheroid. This is about 1 centimeter dimension across the slide. And so when you separate these 4 elements of this spheroidal bed, then you measure their magnetism, you will find that the glass is uniquely paramagnetic, that it shows very enhanced magnetization compared to the limestone grain that are diamagnetic, means that they're in a magnetic field, they are trying to reduce the magnetic field, which is very similar like a white spherules. And the pink spheroids are, because they have a hematite, that's why they have a pink color, you can see that they are just a little bit higher than 0. So they are slightly positive, but uniquely the magnetic enhancement is for the glass. Ejected pink spheroids had temperature of more than 100 Celsius at the time of their deposition. This is because they contain a record of magnetic field that existed at the time of the impact and at the place of their deposition. The evidence for this is just a reminder of the spheroid bed, where for these samples we just collected from this yellow layer, and we choose spheroids that are like between 1 to 2 centimeters in diameter. I mean, what you do, you just measure the magnetic aura, like what's magnetic around them. And when you do that, then you find out that all of them are kind of like clustering with the vector that goes like upward in this east-south direction. So sorry. And so this is an indication that there was that once they deposited, that when they were cooling, they actually acquired magnetization in that direction. There is a spread of the values, and the spread of the values is partly the fact that when we were collecting them in an oriented way, there was a little bit ambiguity, which would explain a little bit of the spread of these values. And of course, when they deposited them, because of the heat contraction, they may also move in place. The reason why there are 2 of these stereo nets with the directions is that normally you are testing if the magnetization is stable. So NRM on the left side is the original magnetization, and then you are trying to clean these spheroids by alternating field to see how stable the signal is, and you can see the signal was pretty stable. It shows also with this blue and orange how it changed between the original magnetization and after the cleaning. Another what we found, that surface of Pook's pebbles was heated to temperature exceeding 600 Celsius. Now, these are not spheroids, these are Pook's pebbles, the big thing like a fist-sized pebbles. And this is because there is evidence of metamorphism of calcite, increased magnetization of the pebbles towards their surfaces, and that magnetization component acquired on their landing. In order to show the evidence, we wanted to know if how well this Pook's pebbles is can acquire magnetic field when you heat it up and acquire magnetization by just cooling in an earth field from high temperature. So we make these pairs like a PP01A and B and PP02A and B, and so the A's are that you measure natural magnetization, then you saturate it, and you look at the values. The B samples are that you actually heat it up and cool in the Earth-like field, and you can see that after the heating and cooling, they actually acquired magnetization more than order of magnitude stronger than its natural magnetization. I hear the ding. And then when you saturate the samples, you can see that there is again like an order of magnitude increase of magnetization. What it means that because of this heating and cooling, the material is capable to create magnetic carriers just because of the heating and cooling. And those magnetic carriers are giving you these extra magnetization that you can see here. Another line of evidence is that we took one of this Pook pebble, as you can see here in oriented way. We cut it in like 3 slices, and we used the middle slice in here, and we just sectioned it on the number of subsamples, and then we just used non-magnetic saw and cut these cubes, from this sample. And then we measured its natural magnetization, and when you look at it, right away you can see that there is this surface that all the surface samples have enhanced magnetization. Of course, you are curious what's going on, right? So you saturate the samples. Now, what I mean is saturate, right? Each magnetic sample or each magnetic object has a level of magnetization, and there is only certain limit. So, for example, if you see this glass, right, you can see there is a water in my flask. And there is about, let's say, 5% of water. I mean, this is the magnetization that is kind of related to this D slide, right? This is a natural magnetization. But once I saturate it, right, I will be putting water in my flask and until it's full, and then I cannot put any more water in it, means saturated. And that's the case of this slide, where you have saturation magnetization. It also shows enhancement along the perimeter of this slice. So this is an indication that there is some kind of a change along towards the surface. When you look at the directions also appear to be to be consistent with the reverse field at the time when this Pook's pebble deposited for this outside, meaning that when it deposited, the surface was hot and was cooling down and acquired magnetization in place that relate to the reverse magnetic field at the time of deposition. Pook's pebble experience interior exposure to strong magnetic fields at various directions, and this is consistent with electric discharges. As I said, normally rocks get only like a fraction of magnetization, like 2%. If you take any object near you and measure its magnetization, you will find it's about 2% of its magnetic field because of the, this is because all objects, I hear the ding, all objects were magnetized in Earth's magnetic field, and so they kind of like remember the Palo intensity. However, in this case, you can see that there is a, so Palo intensity values are the gray values. However, you can see that there is a fairly large variation inside this pebble, and that's indicated that they were magnetized by some anomalous process, and you can see suddenly the corrosivity increase, which means that the material of the Pook's pebble, I mean, there has plenty of high corrosivity carriers, and therefore this is another. Therefore, only low corrosivity magnetic grains were magnetized, and we think that this is another line of evidence for electric discharge for these Pook's pebbles. And these are the conclusions that I was just going through and providing the data or the evidence. And with this, I would like to also thank many people. Without them, this project would not exist, or would be difficult to finish or to get to the final line. And with this, thank you for your attention, and I hope you are still awake.
Thank you, Gunther. That was very interesting. So it looks like we have at least one question over in the chat. Stuart, do you mind
Sure.
reading that out loud for us? Thank you.
So again, since it's the first of the day, I apologize for all mispronunciations. First up is Sean Gulick. Question: if the pebbles were heated to 600 degrees centigrade at the impact site, why would the entire pebble not show a reversed magnetization? Or am I misunderstanding your vision of ejecta and placement process?
Well, thank you for the good question. And when I go back to my slides, let's see if I can do it. Yes. So this is the magnetization of Pebble. So you can see that the only surface was like a heated, and so was changed, was enormously magnetized. So the data in here indicate that it was the only surface samples, or mostly surface samples, that show that there is a prevalence of this direction that was like a reversely magnetized. When you look at this stereonet down there in the lower left corner, you can see that when you take the interior slice, that there is quite a range of variation in direction of magnetization. And so the idea is that it's not the entire pebble that was heated at 600 Celsius. It was just the surface that experienced this increase of temperature. And so when it deposited, the surface cooled down, and but the interior was still cold, because you normally, I mean, the process of ejection and flying through the space, it only took like on the order of 3 minutes to fly from the center of the crater to this location. And so by blasting through the dust that was around it, you would think that you would heat just the surface, but not the interior to 600 degrees C.
All right. The next question is from Matthew Hooper, who asked, does the type of magnetization depend on the target material?
Well, we didn't talk too much about type of magnetization. We only talk about NRM, which is natural magnetization, and saturation magnetization. And so there is one unique way how you can kind of normalize all rocks or all magnetic minerals, which means it doesn't matter if you have hematite, pyrrhotite, greigite, or magnetite. And this is the way that I was speaking, that each rock, no matter what's the magnetic carrier, usually get a certain magnetization. Like in this, if you can see this flask, there is water, right? And so each rock get this like a 2% of magnetization. And the reason is because they were formed by either by cooling in an earth field or chemically precipitating an earth field. And that's usually the signature of every rock, no matter what's the mineral, what the composition. And so that's why we are using this approach that we are comparing this natural intensity with the saturation intensity, and that gives us a way how we can normalize. We don't need to like worry what kind of a magnetic carrier we have in our rocks.